Consider this mountain biker traveling through this rough terrain. Given this video, how can we understand his behaviors? We may be able to recognize this as a mountain biking. How about the more detail, such as physics of activities? In order to understand the physics of activity, we need to extract the gravitational force that affected his motion, which requires to wear the gyroscope in his body. For speed, we need to wear accelerometers. For control, we need to recognize pedaling and braking activities, which is almost impossible to recognize from this view. If we have multiple cameras on the bike, we may be able to recognize it. A question that I would like to ask with this paper is, if I have a first-person camera that can provide direct access to the visual sensation, can we understand the physics of activity without external sensors? This is a first-person video of the mountain bikers. This video stimulates our visual sensation, which allows us to understand where it's going. At the same time, this video also stimulate our physical sensation, which allows us to understand how much force is applied to him and how he controls his bike to balance his posture. In this paper, we present a method to decode the physical sensation in the form of force and torque from the first-person video. For instance, we compute the gravity, roll torque to balance his posture, the thrust force applies through the braking and pedaling, and air drag as well. On the right, I'm showing a 3D reconstruction of the camera trajectory of the mountain biker. On the left, I visualize all force and torque that apply to him to balance and move forward from the first-person video. This is a 3D reconstruction which allows us to understand the geometric relationship between camera and 3D points. The question is whether the geometry or kinematics is enough to understand bikers' behaviors. Unfortunately, it's not, because it does not tell what caused this motion. Then what is the key factor to cause this motion? Consider this a first-person image. This image is quite interesting because this tells us about the body orientation of the camera wearer. This indicates a very interesting, important factor of the motion, which is gravitational force. Gravitational force is the main driving force to cause a motion. Then how to compute this gravity from the image? Gravity Q exists in nature. For instance, tree grows vertically. The surface normal of the water align with the gravity direction, and the gravity is perpendicular to the horizon. Therefore, we can directly learn the visual semantics of the gravity from the images. Here, we predict the likelihood of the gravity using a convolutional neural network, which produces about the 0.5 degree error. The predicted gravity in image is ambiguous in 3D, which can be resolved by taking into account multiple frames. Therefore, we can reconstruct the gravitational force in three-dimensional space. At this moment, the body orientation is tilted. Then how can he even balance it at this posture? He can balance his posture because he moved fast enough to compensate the gravity. So the speed is a main key point to estimate the balance. Then how can we estimate the speed? Speed can be trivially computed by taking time derivative of the camera trajectories. However, this is not true because structure from motion is a genuine scale ambiguity. Scale factor alpha cannot be directly estimated from the structure from motion without external sensors or calibrations. But we found a very interesting relationship when the biker turned a corner. He has to balance between the gravitational force and centripetal force with a bank angle theta. And the centripetal force is a linear function of the scale factor alpha. Therefore, we can solve for the scale factor alpha because the gravitational acceleration is always constant, 9.8 meter per second squares, and the centripetal force can be measured by the structure from motion. Therefore, we can recover the true scale of the reconstruction for the biking activities. So here I visualize the physical scale of the elevation and speed measured by the structure from motion, measured by this first person video. Note that this reconstruction is physically meaningful as the typical speed of the mountain biking ranges between 1 to 10 meters per second. The forces applied through the braking and pedaling. Then how to compute these control parameters from these videos? The forces applied to the center of mass, which affect the linear acceleration of the center of mass. The force can be decomposed into passive and active forces. The passive force is a force applied from the environment, such as gravitational force, friction force, and air drag. Active force is a force applied by the mountain biker through the braking and pedaling. In the same way, we can decompose the torque into the passive and active components. These two equations tell us about the equation of motion for the center of mass. Therefore, we can describe the center of mass using a force and torque by solving this ordinary differential equation. We approximate the center of mass using a camera center, which we can reconstruct in structure from motion. This approximation is valid as speed goes high. We formulate this problem as a structure from motion, parameterized by force and torque by solving ordinary differential equation. Together with the temporal regularization, this problem becomes inverse control problem embedded in structure from motion. Here we evaluate our system with body-mounted cameras and IMU. This is a ground truth gravity direction measured by the IMU. Y-axis of camera is a good predictor because the cameras are often oriented upright. This prediction can be improved by taking into account the multiple frames. Surface normal of ground plane is not actually a good predictor because the ground plane is often tilted. Our method that uses a convolution neural network to predict the gravity direction outperforms all other methods which produce a less than 2-degree error. How about the scale? We compare our scale with the ground truth scale measured by the IMU. Here, I plot the scale ratio between our system and IMU for 11 different sequences. It produces about 1, which indicates that two scales are almost similar. How about control? We recognize pedaling and braking activity but note that measuring acceleration and deceleration directly from structure from motion is not sufficient because the force needs to be decomposed into passive and active forces to recognize activities. Optical flow-based method produces unconvincing result because it is completely ignorant of the 3D motion and the physical force interactions. Structure from motion or IMU-based method produce a little bit better because it knows the gravity and 3D motion. Ours performs all other methods because our system is aware of the absolute scale, absolute orientation by gravity, and the force interactions. Here, we predict the forces and torque to another biking activities. We predict the gravity, force and torque, and air drag as well. On the right, I'm showing a 3D reconstruction of the camera trajectory of the mountain biker. This reconstruction is physically meaningful as the typical speed of the mountain biking range between 1 to 10 meters per second. The same dynamics can be applied for the skiing activity, where the skier making a number of the banking ton, which is reflected onto the thrust force and roll torque. Also, we can apply to the jet skiing activity, where we can observe high thrust force and air drag. A base jumper jumps from the cliff of the mountain and flies through the mountain valley. Our system recognizes high lifting force and air drag. In the same time, the direction of the lateral force tells us about the turning direction in the future. In this paper, we present a method to decode the physical sensation from first-person camera, which allow us to understand the internal state of the camera wearer. We don't need the external sensors. We don't need a third-person camera to observe ourselves. Thank you.